Hi, my name is Puriya Darakhshanfar and I am a PhD student at Delft University of Technology. This video will present our recent study about a novel secondary objective called basic block coverage, which complements the guidance provided by approach level and branch distance in the search-based software test generation. Let's start with a motivating example. Here we have a method called FromMap, which is collected from XWiki, a complex open source wiki system. Assume that our goal is generating a test case that covers line 409 in this method. The reason for covering this line can be different. It can be for increasing the structural coverage, or it can be for something like crash reproduction that you need to cover some specific paths. For the test generation, we want to use a genetic algorithm in which each generated individual in the population is a test case or test suite. The search process in the algorithm is guided by one or more fitness functions. In this example, first we generate a set of random tests. Then we use a fitness function called line coverage to measure the distance of each of these test cases from covering line 409. In previous studies of search-based test generation, usually line coverage is calculated by two very well-known heuristics called approach level and branch distance. To calculate the approach level and branch distance, first we produce the control flow graph of the method. Here the method is FromMap. A control flow graph is a directed graph in which each edge shows the flow of the method, and each node is a basic block. A basic block is a sequence of statements that there is no branch among them. So theoretically, if a test case executes the first statement in a basic block, it will cover the other statements in this basic block as well. For instance, lines 404 to 406 is a basic block because a simple test case can cover lines 404 to 406 without facing any branching. Then we indicate the target node. In this graph, the target node is the basic block containing the target line. Next, we find the nodes on which the target node is control dependent. The target node is control dependent on the nodes that contain a branch which is capable of changing the execution path away from reaching the target node. For instance, node 409 is control dependent on node 403 because line 403 contains a condition for a for loop that if it is not fulfilled, we directly go to line 417 and we miss the chance to cover the target line. Then we check the execution path of the generated test. For instance, here, the yellow path is our execution path. The approach level is the number of uncovered control-dependent nodes. Here, there are two. And finally, for branch distance, we look at the condition of the last covered control-dependent node, the condition that took the execution path away from reaching to the target line. The branch distance will be a value between 0 and 1 according to the condition in this control-dependent node. As we can see, both of these heuristics are only checking the control-dependent nodes. But something is missing here, implicit branches. Assume that we have a test case that its execution leads to a null pointer exception in line 404. So the execution is stopped in this node and it cannot reach the target line. But we don't have any indication from the control-dependent nodes. Now, assume that we generate another test that throws null pointer exception in the next line. Clearly, the second test case is closer to covering the target line. However, since approach level and branch distance does not consider implicit branches, the distance of these two test cases from the target node is the same according to these two heuristics. So we have an issue here, because this problem can lead to a flat landscape in the search space. We know that a flat landscape means that we don't have any guidance on that point in the search space. One solution to address this problem is testability transformation. In this technique, we need a pre-analysis process to detect the implicit branches, and then we can transform the bytecode to consider those branches as well. But this analysis is costly, especially if we have lots of couplings. So if we have lots of method calls to other classes, then we need to detect the implicit branches in those classes as well. Here in this study, we introduce a new and simple strategy to tackle this issue. In this approach, we define a new secondary objective called basic block coverage, or in short BBC, which complements the guidance provided by approach level and branch distance. Since BBC is a secondary objective, it is only be used when we have two test cases with the same value for our line coverage fitness function. So the inputs are two test cases with the same fitness function value, and also the target method and target line. And the output is an integer. If BBC returns a negative value, the first given test is closer to the target line. If it returns a positive value, it is the opposite and the second test is closer. And if the returned output is 0, we don't have any preference for these two tests. Let's see how BBC works. First, for each of the given test cases, we identify the fully covered basic blocks between the last covered control-dependent node and the next uncovered control-dependent node or the target line. Fully covered means that the execution path covered both the first and the last statements in the basic block. Then, we identify the semi-covered basic blocks. Semi-covered blocks means that the execution path covered the first statement but not the last one in the basic block. Next, we check if both fully and semi-covered basic blocks of a test case is a subset of the other ones. If this is the case, we know that the test case with more covered blocks is the closer one, so we return a value that indicates the winner. The next possibility is that both of the test cases have the same fully and semi-covered basic blocks. In this case, we need to go deeper. First, we find the closest semi-covered basic block to the next uncovered control-dependent node or the target line. Then, we check the lines covered by each of the tests in the basic block. The test case with more coverage is the winner. If they both have the same coverage, then we return 0. Finally, if we don't have the two mentioned conditions, it means that we have more than one path from the last covered control-dependent node to the next uncovered control-dependent node or the target line, and each of the given tests took a different path. So we cannot really indicate the winner because we don't know which path is the best for achieving the target line. Before showing the results regarding our evaluation of basic block coverage, we need to talk about one of the techniques in which approach level and branch distance are used for guiding the search process. Search-Based Crash Reproduction. When a user operates a piece of software, it is always possible that he or she makes the software crash. In the crash report, we usually have a stack trace, which indicates the active method calls during the crash happening. The goal of Search-Based Crash Reproduction is to get a stack trace and the application in which the crash happened, and then perform a search process to generate a test case that its execution leads to the same stack trace as the given one. The fitness function in this algorithm can be defined in various ways. The first one is called weighted sum crash distance. This fitness function contains three elements: line coverage, exception coverage, and stack trace similarity. In the first element, we produce the control flow graph of the method that appeared in the outmost frame of the given stack trace, here method M0. Then, this heuristic measures the distance of the test execution path from covering the target line, the line number which appears in outmost line of the given stack trace. This measurement is done by approach level and branch distance. After covering the target line, the value of the first heuristic will be 0, so it is time to move to the second heuristic. This heuristic checks if we have thrown a stack trace after covering the target line or not. If the generated test throws the same type of exception as the given one, this heuristic is fulfilled as well, and we move to the third heuristic. Here we know that we have thrown a stack trace after covering the target line, so it's time to compare the other frames of a thrown stack trace by the test with the frames of the given stack trace. If they are the same, the last heuristic is fulfilled and the fitness value will be 0. The other way to measure the fitness of the test cases generated by the search process is called ST distance. This fitness function was originally introduced as one of the elements of a bigger fitness function for reproducing crashes from the core dump. But since we don't always have a core dump due to the privacy violation, in this study we only implemented the ST distance element, which only works according to a given stack trace. This fitness function is more relied on the approach level and branch distance. It first measures the line coverage to the outmost frame using these two heuristics. After covering the first frame, it repeats the same procedure for the next frame. It covers all of the frames using approach level and branch distance one by one. And after covering all of the frames, it checks if the thrown exception is the same as the given one. In this study, we assessed BBC in search-based crash reproduction. Our baselines are search-based crash reproduction guided by weighted sum and crash reproduction guided by ST distance. And in our novel approach, we add BBC as a secondary objective of each of these fitness functions. We implemented all of these four configurations in Botsing, an open-source search-based crash reproduction framework. We applied all of these techniques on 124 non-trivial crashes collected from JCrashBack, a benchmark for Java crashes. Due to the randomness in search-based algorithms, we repeated each execution for 30 times. We set the time budget to 5 minutes. So in total, our evaluation contains about 115,000 executions that each of them takes 5 minutes to execute. In this study, we tried to answer two research questions. The first research question analyzes if BBC can improve the crash reproduction ability of the search process. And the second research question evaluates the impact of BBC on the amount of time needed by each search algorithm to reproduce a crash. To answer the first research question, we performed a pairwise comparison of the impact of BBC on each fitness function in terms of the number of times a search algorithm can reproduce a crash. For calculating the impact factor, we use the odds ratio because of the binary distribution of crash reproduction results. Crash is either reproduced or not. To identify the significant cases, we performed the Fisher's exact test. The results indicate that applying basic block coverage can significantly improve the crash reproduction guided by ST distance in 5 crashes. This number is 1 for the weighted sum fitness function. This result was expected because ST distance uses approach level and branch distance more often. We even observed that BBC helped ST distance reproduce some crashes which were not reproducible by other configurations, for instance XPK 13377. If you check this crash, you can see that the method we used as an example at the first slide of this presentation is involved in this crash. For research question 2, we measured the impact factor using Varga-Delaunay statistics and assessed the significance of results by the non-parametric Wilcoxon rank sum test. Here we can see that BBC improves the efficiency of the search process guided by ST distance in 33 cases. As we can see, in 32 crashes, the impact was either large or medium. We can also see that BBC improves the efficiency of weighted sum in 17 crashes with large or medium impact. In both cases, on average, the improvement achieved by BBC in significant cases is about 50%. In this study, we observed that BBC helped approach level and branch distance. Hence, in our future works, we want to assess the impact of this secondary objective on other search-based test generation techniques which are using approach level and branch distance as well. Techniques such as search-based unit testing or integration testing. The implementation of all of the crash reproduction approaches we use in this study is available in the BotSync repository. Also, the replication package of this study is openly available in Zenodo. Thank you very much for watching this video and goodbye.